In session 2, we learned about the 3 stages of responding. First, we identify the stimulus. Then, we select the appropriate response needed for that stimulus. And finally, we actually execute the response. We saw in the assignment task and the Stroop task that irrelevant information of a stimulus affected response times. But what about irrelevant information or irrelevant stimuli in the environment itself? In other words, when you selectively attend to a stimulus, there are things about that stimulus that don't matter to you, like the location of the stimulus in the assignment task. But that stimulus is unlikely to appear in isolation in real life. The stimulus you're paying attention to is surrounded by other stimuli. So do those other stimuli affect your response as well? Well, yes, they do. The first stage of identifying the stimulus is affected by the context in which the stimulus is presented. Palmer was the first to investigate the effect of context on stimulus identification. This suggests that there's a top-down element to stimulus identification. If we identify another stimulus first, we are then, if you will, in the zone to identify related stimuli. These context tasks are often called priming tasks, where the context is the prime. Now, the term prime here stems from the Latin word for first. So basically, we are presented with the context first before we are asked to identify the target. But now we're faced with a difficult problem. We need to find a way to measure the speed of stimulus identification. Just asking people, do you recognize this stimulus, isn't going to help much. People just blankly stare at the screen and just press yes over and over. So we need to find a creative solution to this problem. Well, we can do that using words. Well, obviously we can't just, again, ask, do you recognize this word? No, we have to throw in some nonsense words to make it a bit more difficult. And now, we'll ask people to tell us whether the word is an actual word in English or not. Now, we do this in a task called the Lexical Decision task. Now we need to find a way to ask this question within a context, a prime. So each trial shows the participant 2 words. The first word will be our prime, our context word. And participants respond to that word by telling us if it's English or not. Now they have to respond to the prime as well. Otherwise, they'll just stop paying attention to it. So once they've responded to the prime, we show them the target to which they respond as well. And the idea here is, of course, that the prime is either related or not related to the target. And if it is related, people respond faster to the target. But there are still many questions that remain to be answered when it comes to priming. For example, does a related prime help you, or is it actually the case that the unrelated prime confuses you, or maybe some odd combination of both? How long does the priming effect actually last, and what happens to the strength of the priming effect over time? We are still trying to figure out these questions. Now, in session 3, we discussed memory and the importance of memory. But we haven't really talked yet about how memories are exactly stored. Are memories simply stored chronologically? Or what about language? Are all the words you know stored like in a dictionary? Are words stored according to their orthography, which is the way that the word is written? Or maybe phonologically, which is the way that a word sounds? Or maybe semantically, which is according to its meaning? Well, these are also big questions which we haven't really figured out yet, but we do have a lot of ideas. According to Collins and Quillian in 1969, our knowledge is stored in semantic networks. So let's take the word canary. we have a semantic understanding of that word. We know the features of the concept canary. It's an animal, and more specifically, it's a bird. It has wings, can sing, is yellow. So all the concepts we know are stored according to their semantic features in relationship to one another. Now, as you can see, the semantic network has a hierarchical structure. So if a concept like canary belongs to the category bird, it also belongs to the category animal. There is also the principle of inheritance. This means that a feature is only stored once in the network. This also means that the feature must be stored as high as possible in the hierarchy, so that the feature can apply to everything that is stored beneath it in the network. In other words, the feature has wings is applied to both canary and ostrich, because has wings is stored higher than both, and both canary and ostrich inherit that feature. Note that inheritance of a feature can nonetheless be negated on a lower level. So the feature can fly is stored at the level bird, and so can fly will be inherited by both canary and ostrich. But ostriches can't fly, so the inherited feature is then negated in the ostrich node by storing the feature cannot fly. Now we can test the Collins and Quillian model using a task called sentence verification. Now people are asked to verify a feature about a concept. For example, they're shown a sentence like a bird has wings, and they must decide whether the sentence is true or false. Now the closer the two concepts or features in the sentence are within the semantic network, the faster people respond. So you'll be quicker to confirm the truth of a sentence, a canary can sing, than the truth of a sentence, a canary is a bird. And you'll take even longer to respond to the sentence, a canary is an animal. Now that's great when the sentence is true, but what happens when the sentence isn't true? Well, in that scenario, the closeness in the network actually leads to problems and errors. When features overlap, it takes more time to realize that a sentence is not true. So we see the exact opposite effect on our response times here. In short, when the sentence is true, you're quicker the more features overlap. And when the sentence is false, you're slower when features overlap. Finally, keep in mind that there is something called the typicality effect. People respond quicker to sentences like a robin is a bird than to a chicken is a bird. This is because the robin is a more typical example of a bird than a chicken. This typicality effect shows us that there's more to it than just the semantic network distances. So the semantic network model by Collins and Quillian is limited and doesn't tell us the entire story. Now you'll learn more about this in future courses on psycholinguistics. One final note. There was some confusion as to why a repeated measures analysis was used when testing for a difference between the semantic distances. After all, a repeated measures analysis suggests that we repeated some task or measure. But a repeated measures analysis is simply a different way of saying within subjects analysis. And in this case, the design is a within subjects design, because all participants did trials with all possible semantic distances. It is essentially an expansion of the paired samples analysis, but we're comparing more variables than just one pair of two variables. If we only measured two distances, we could use a paired samples t-test. But because we measured three distances, we cannot form a single pair to test everything in one go. Now we could form different pairs between the possible variables and test those one after another and get the same analysis, but with a repeated measures analysis, we are doing the same thing as a paired samples analysis, except we can include all of the variables, in this case distances, at the same time in one analysis. There's also something called sphericity. Sphericity is tested using Mauchly's test of sphericity, which is automatically produced for us in the output by SPSS. Sphericity refers to the variance of the differences between the measured data on each variable. Now we can compute the variance between the response times for distance 0 and distance 1, for example, as well as between distance 1 and distance 2, and so on. Now Mauchly's test tells us if these variances are the same or different, because we'd expect them to be the same. Now if Mauchly's test is non-significant, it suggests that the variances are the same, so we can assume sphericity. If Mauchly's test is significant, however, we need to correct for the violation of the sphericity assumption. Now this is rather advanced, and you'll learn more about this in statistic courses in the future, but it's good to keep in mind for now. And that's basically it for our 4 sessions. I hope these videos have been helpful to you in reviewing the material from the syllabus. Good luck on the exam.